Welcome back to our electrons unit. You will need your periodic table for this video. Electrons are organized in energy levels of positive integer value, n equals 1, 2, 3, etc. These are also called principal quantum numbers. They roughly correspond to period numbers on the periodic table. So energy level number 1 corresponds to period 1, energy level number 2 to period 2, energy level number 3 to period 3, etc. Within each energy level are sublevels, and they are designated by the letters S, P, D, or F. And these correspond to blocks on the periodic table. So here are the locations of the S, P, D, and F blocks. For the purposes of electron configurations, helium belongs here on the periodic table, and here is the S block. Then we have the P block here to the right. In the middle over here, we have the D block. And finally, on the bottom here, we have the F block. Each sublevel also corresponds to a certain electron cloud shape, which is called an atomic orbital. What do the atomic orbitals look like? They are a 3D region around the nucleus, and they tell us where there is a high probability of finding an electron. So the S orbital over here is a spherical shape, the P orbitals are a dumbbell shape, and the D orbitals look like four-leaf clovers, except one is a little bit different here. Now, each orbital can hold a maximum of 2 electrons. An S sublevel contains only one S orbital. So how many total electrons can fit in an S sublevel? That would be 2. A P sublevel contains 3 P orbitals, so a total of 6 electrons. A D sublevel contains 5 D orbitals, so there would be a total of 10 electrons. And finally, an F sublevel contains 7 orbitals, so there would be a total of 14 electrons. We go back to our S, P, D, and F blocks. So if I have the S block over here, and let's say I pick energy level number 2, there is an S orbital, and it can hold 1, 2 electrons. If I go to my P block, and I pick an energy level, I have 1, 2, 3 orbitals. So 1, 2, 3, 4, 5, 6 electrons. Go to my D block over here. Now pick an energy level. I would have 1, 2, 3, 4, 5 orbitals with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Finally, the F block, 1, 2, 3, 4, 5, 6, 7 orbitals, 14 electrons. Electron configurations and orbital diagrams. What are these? Methods used to represent the arrangement of electrons in an atom. 3 rules govern the filling of atomic orbitals. First, the Aufbau principle, the Pauli exclusion principle, and Hund's rule. The Aufbau principle. Electrons enter orbitals of lowest energy first. The Aufbau order lists the orbitals from lowest to highest energy. You do not have to memorize this order because you can read it on the periodic table like a book. First, let's see what the letters and numbers mean. So for example, if we had 3p6, the 3 here represents the energy level. The P is the sublevel, and the little 6 over here is the number of electrons. So how do we read the Aufbau order? We read it like a book on the periodic table from left to right and from top to bottom. So if we start with a hydrogen at 1, we have here 1s and 2s, 3s, 4s, 5s, 6s, and 7s. And for the P block, we have 2p, 3p, 4p, 5p, 6p, and 7p. Notice that the energy level and the period number correspond for the p and the s blocks. For the d block, we have 3d, 4d, 5d, and 6d. Now you have to notice that for the d block, it is the period number -1. So when we get to period number 4, we have 3d, not 4d. Finally, for the F block, we start at 4F and 5F. The other thing you need to notice is when we get to barium here, it's element number 56, and then we jump to element number 71. So the F block actually fits over here after barium. And if we look at radium, element number 88, then we switch to 103, so we have to go to 89 over here before we can go on. And you will notice that here we have 57 through 70, and then we go back to 71. So really the F block fits here in between the S and the D block. Now when we read our order like a book, we start at hydrogen, we have 1s1, then 1s2 for helium. Then we go down one level, 2s1, 2s2. Then we go 2p1 through 2p6, 3s1, 3s2, 3p1 through 3p6, 4s1, 4s2. Then notice after 4s comes 3d, 3d1 through 3d10. Then 4p1 through 4p6, and etc. And then when you get to the 6s, you have 6s2, and then you have to switch to F, 4f1 through 4f14, and then you are back to 5d1 through 5d10, and 6p1 through 6p6, and so on. Pauli exclusion principle. It states that an atomic orbital may hold at most 2 electrons, and they must have opposite spins called paired spins. There is an electron with a spin. It's an arrow pointing up or an arrow pointing down for the opposite spin. An orbital can be written as a block or a line. So there's a block with the 2 arrows pointing up and down, or you could draw them on a line with 1 arrow up and 1 arrow down, and the line represents an orbital. Hund's rule states that orbitals of equal energy, such as 3 2p orbitals, are each occupied by 1 electron before any orbital is occupied by a second electron, and all electrons in singly occupied orbitals must have the same spin state. What this means is that when you have orbitals such as p orbitals, which all have the same energy, for example, 2p will all have the same energy. When the electrons come in, they come in singly, and they have the same spin state. So it would be wrong to make them go singly and then double up here before you put a single one here. So that arrow should not have gone here. So let's take a look at how we fill 2, 3, and 4 electrons in a p sublevel. So if we have 2 electrons, they go in singly, one and then the other in the same spin state. Then we have 3 electrons, again they go up one by one, singly, same spin state. If we have 4, we would go 1, 2, 3, and then we can double up in the opposite spin state. Now let's draw some electron configurations. So let's start with carbon over here. Carbon has 6 electrons because its atomic number is 6. So if we draw its electron configuration, we're going to write the Aufbau order until we reach carbon. So we start with hydrogen and we cover 1s1 and 1s2. Remember, helium is over here. So 1s2. Then we go to the next line. We have 2s2 and we have reached beryllium. 2s2. Then we continue and we cover boron, and now we have reached carbon. Here is 2p, and we have 2 for carbon. Now let's do selenium. It's over here at number 34. 1s2, 1s2, 2s2, 2s2. I continue. 2p6, 2p6, 3s2, 3s2, 3p6, 4s2, and then I get to D. Remember, D starts at 3, 4 minus 1. So 3D all the way to 3D10. And then I reach 4P over here. So 4P, 1, 2, 3, 4. We have an electron configuration. How do we figure out what element it is? So what you do is you look at the last one over here. If we have 3D3, I can go find 3D3 on my periodic table. 3D starts here. So 3D1, 3D2, 3D3, and I have vanadium. On number 2, I have 5s2 as my last one over here. So 5s is over here. And 5s2 will be strontium. How do we draw orbital diagrams? It is easier to first write the electron configuration and then draw your orbital diagram. So let's do carbon. Carbon is over here. It is 1s2, 2s2, and 2p2. Then I know that my s sublevel has 1 orbital, so I draw a line for an s orbital. I have another s sublevel, 1 orbital. P sublevels have 3 orbitals, so I draw 1, 2, 3 orbitals for my p sublevel. Now I fill those with the electrons. So I have 2 electrons. Remember that when I have 1s2, this is the energy level, the number 1, sublevel, and number of electrons. So 2 electrons, they have to have opposite spins to follow Pauli's exclusion principle. Another s orbital with 2 electrons, and a p orbital with also 2 electrons. And remember Hund's rule, they have to go in singly before they can double up. Finally, let's do iron. Over here at number 26, electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. 1 orbital for s, 2 electrons. 1, 2. 1 orbital for s, 2 electrons. 1, 2. 3 orbitals for p. 1, 2, 3. We go up singly. 1, 2, 3, and we double up 4, 5, 6. 1 orbital for s, 2 electrons. 3 orbitals for p. We go up singly. 1, 2, 3, 4, 5, 6. 1 orbital for s, 1, 2 electrons. And 5 orbitals for d. 1, 2, 3, 4, 5. And I have 6 electrons, so I go singly 1, 2, 3, 4, 5, and then I can double up. This concludes our video for today. I hope you have taken good notes. Come to class prepared with your questions.